Hello students, in today's lecture we will quickly discuss all the numericals related to Newton ring formula. Let us first quickly revise the formulas before attempting the numericals. So interference topic, Newton ring formula, fringe width omega is equal to lambda upon 2 mu theta. This is for normal incidence. Theta is the angle of a wedge that is formed by a medium. Mu is refractive index and lambda is wavelength. Wedge angle theta is given by n lambda upon 2 mu into xn2 minus xn1, where xn1 and xn2 are the position of dark fringes which are situated at points P and Q. N is the order of the fringe, lambda is the wavelength. Diameter of bright rings are proportional to square root of odd natural numbers. This is asked in theory also and in numericals also. For dark rings, diameter is given by under root 4n lambda r. N is 0, 1, 2, 3, etc. The wavelength in Newton ring apparatus lambda is equal to dn plus p square minus dn square upon 4pr. Refractive index of a liquid mu is given by dn plus p square minus dn square in air upon the same square in medium or liquid like oil or water. Now, Newton's rings formed by two curved surfaces which are kept like this. Then for dark ring, it is 1 upon R1 minus 1 upon R2 is equal to 4n lambda upon dn square. For bright ring, 1 upon R1 minus 1 upon R2 is equal to 2 into 2n minus 1 lambda upon dn square. When both the lenses are kept in this manner, that the thickness becomes the sum of these two thin layers, then the dark ring, it is 1 upon R1 plus 1 upon R2 equal to 4n lambda upon dn square. And for bright ring, it is equal to 2 into 2n minus 1 lambda upon dn square. Few constants which you should know before starting numericals on Newton ring are 1 angstrom is 10 to the power of minus 10 meter or 10 to the power of minus 8 centimeter. 10 millimeter is 1 centimeter. Pi 3.14. 1 degree is 3600 seconds, and one general formula, angle is equal to arc upon radius. Let us begin. Light of wavelength 6000 angstrom is falling normally on a thin wedge-shaped film whose refractive index has been given to you, and you have been told that the fringes are 2 millimeter apart. You have to simply find the angle of the wedge. So it is very simple. Omega is lambda upon 2 mu theta. Lambda is given to you as 6000 angstrom. Change it into centimeter. Mu is 1.4 and fringe width omega is 2 millimeter. So you change that into centimeter. Put all these values, you get the answer in radians. Now, pi radians is equal to 180 degree. So 10.71 radians is 180 upon pi into 10.7 degrees. This much you multiply and you get the answer in degrees. Next, 1 degree is 3600 seconds. So theta becomes equal to, in seconds, they are asking the answer. So this much multiplied by 3600. Two glass plates enclose a wedge-shaped air film touching at one edge and separated by a wire of 0.05 millimeter diameter at a distance of 15 meter from the edge. You have to find the fringe width. Monochromatic light wavelength has been given to you. Again, they have told that it is falling normally. So once again, omega is equal to lambda upon 2 theta. Now look at this figure. We will use the formula tan theta, or you use angle is equal to arc upon radius. So it becomes AB upon OA. AB is 0.5 mm, 0.005 centimeter, and this 15 centimeter has been given to you. Lambda is 6000 angstrom. Change it into centimeters. First unify the units and then just put the values. two plane glass surfaces in contact along one edge are separated by at the opposite edge by a thin wire of 20. If 20 fringes are observed between these edges in sodium light for normal incidence, what is the thickness of the wire? See, in the numerical itself, they give you the condition for normal incidence. So let us see the diagram. See, this will be the thickness of the wire. This will be the length of the glass surface here. And omega is equal to lambda upon 2 theta. Let T be thickness of the wire, X be the length of glass surface at point of contact. So simple angle, or you can even say tan theta is perpendicular upon base and assume tan theta approximately equal to theta, or angle is arc upon radius. So you get T upon X. Putting these values in the formula of omega, let n fringes be seen in the entire film. Then X is equal to n omega. Simply put here in value of omega, you get your answer. You change angstrom into centimeter and you get the answer. Next, between two optically plane glass plates at one edge, a foil is introduced to get a wedge-shaped air film viewed in mercury green light, whose wavelength has been given to you along the normal. We see 12 fringes. You have to find angle of wedge, thickness, and fringe width, and refractive index of water has been given to you. Now, spacing between 12 fringes has been given to us. So 12 omega is equal to this much. So omega is 0.4 upon 12. Now the fringe width in air for normal incidences, omega is equal to lambda upon 2 theta. Theta is lambda upon 2 omega. You put this value of lambda, put the value of omega, you get the answer in radians. You can leave it in radians if they are not asking you to convert it in seconds. Let T be thickness of foil, L be the length of plate. Then once again, angle is T upon L. So T is theta L, put L and T and you get the answer. You can change your answer, leave it as centimeter. If theta is angle of wedge formed by a medium of refractive index mu, then for normal incidence, omega dash is lambda upon 2 mu theta. For water, refractive index is 1.33. Put the values and you get your omega dash. Two plain rectangular pieces of glass are in contact at one edge and separated by hair at the opposite edge, so that a wedge is formed. So when light of wavelength 6000 angstrom is falling, normally 9 interference fringes are observed. What is the thickness of the hair? So the fringe width is omega equal to lambda upon 2 theta, and theta is T upon X. You can see I have drawn it in the figure here for you. N fringes are seen, so X is equal to N omega. Put this value here in this expression for omega. So T becomes equal to N lambda by 2. Now N is 9, lambda is 6000 angstrom. Straight away put the value and you get your answer. Leave it in angstrom if the question is not specifying which unit they want the answer. A square piece of cellophane film with index of refraction 1.5 has a wedge-shaped section. Its thickness in two opposite sizes T1, T2. Number of fringes appearing is this much, 10. You have to find the difference. Now see, in order that the fringes appear at one end of the film be n, then order of the fringe appearing at the other end will be n plus 10, because the question is saying 10. Now for nth and n plus 10th dark fringe, we use the condition of path difference, and 2 mu t cos r equal to n lambda, and 2 mu t2 cos r is equal to n plus 10 lambda. Just subtract these two equations so that it becomes more simple. Since the fringes are seen normally, angle of wedge is very small, so r is equal to 0 and cos 0 is 1. So this equation reduces to 2 mu into T2 minus T1 is equal to 10 lambda. T2 minus T1 becomes equal to this much. Mu has been given to you as 1.5. Lambda 6000 angstrom. Change it into centimeters. Put the value and you get the answer. Newton's rings are observed with sodium light between a plane surface and convex lens whose separation from the surface can be varied. You have to find the minimum separation beyond which the rings would be invisible, and you have to explain the reason. For this, let us assume lambda 1, lambda 2 to be the wavelengths of D1 and D2 lines respectively. Now at point of contact of lens and glass plate, the path difference between the interfering waves due to both wavelengths is very small, and the ring system due to lambda1 and lambda2 almost coincide. So on increasing the separation between the lens and the plate, path difference increases and ring systems due to both wavelengths appear separated. When bright ring due to lambda1 is coinciding with dark ring due to lambda2 or vice versa, the ring system is going to disappear and you will find a uniform illumination. Now, when this happens, then the separation between the lens and plate at the center, you assume it as T and simply put them in the value of path difference formula. For interfering rays at the center, 2t plus lambda 1 by 2 and 2t plus lambda 2 by 2. Additional path difference is due to reflection at the plate. Now, for disappearance of rings, we will assume 2t plus lambda 1 by 2 equal to n lambda 1 for maxima due to lambda 1 and 2t plus lambda 2 equal to 2n plus 1 lambda 2 for minima due to lambda 2. And we solve these equations, putting these values, we just simplify, we put this equation in this and this equation further simplify, we get t equal to lambda 1 lambda 2 divided by 4 into lambda 1 minus lambda 2, and lambda has been taken as the mean of both, and putting the numerical values, we get the answer. If the angle of wedge is 0.25 degree of arc and wavelength of sodium lines are 5896 angstroms, find the distance from the apex of the wedge at which maxima due to each wavelength first coincide. Let T be thickness of wedge at a point where maxima due to lambda 1 and lambda 2 coincide. When viewed by reflected light, for normal incidence and air film, this condition is given by, we have used it in the previous question also, 2t is equal to 2n plus 1 lambda 1 by 2 and 2n plus 3 lambda 2 by 2. And we find the n value, put this value of n in this above equation here, this equation, and just simplify it further so that expression becomes more simple. Put the values here, simplify, cross multiply. Let theta be angle of wedge and x the distance of the apex angle. So tan theta is t upon x, t is equal to x tan theta. For small values, tan theta can be approximated to theta and t is equal to x theta. Now, 180 degrees pi radians. So 0.25 degrees pi upon 180 into 2.25 radians. You just put this value here, simple. You have been given x1, lambda 1 and lambda 2, pi 3.14, and you get your answer for x as 6.63 centimeters. In Newton ring experiment, the diameter of 4th and 12th ring has been given to you. You have to find the diameter of the 20th ring. So the very famous formula of Newton ring is dn plus p square minus dn square is equal to 4p lambda r. N will be 4, here you have been given, and n plus p will be 12. 4th ring and the 12th dark ring. So their diameters have been given to you. P will be n plus p minus n, that is 12 minus 4 is equal to 8. Simply put the values and either divide to simplify the expression, whichever way you feel convenient, whichever way you find that it is very easy to come to the answer, and you get your answer for diameter. Newton's rings are formed in reflected light of wavelength 6000 angstrom with liquid which is kept in between the surfaces. Now, if diameter of the 6th bright ring is given and radius of curvature of the curved surface has been given, you have to find the refractive index of this liquid. So the formula for diameter of nth bright ring is dn square is equal to 2 into 2n minus 1 into lambda r divided by mu. What have you to find? You have to find the refractive index. So you make this formula in terms of mu. Mu is equal to 2 into 2n minus 1 lambda r upon dn square. In numerical, n is 6, lambda 6000 angstrom. Change it into centimeters. R 100 centimeter. 5th the diameter 3.1 millimeter, change it into centimeter. 10 millimeter is 1 centimeter. Uniform all the units, put them in the formula and you get your answer. In an arrangement for observing Newton's ring with two different media between glass surfaces, nth rings have diameters as 10:7. You have to find the ratio of refractive indices. You use the formula for diameter of nth bright ring as dn square is equal to 2 into 2n minus 1 lambda r upon mu for first medium, and for the second, simply divide. All these terms will get cancelled. You will be left with inverse ratio of refractive index. And you have been given them as 10:7. So when you will inverse it here, it will become 7:10 because they have become in inverse, and you simply get the answer. Newton's rings are made with light of this much wavelength and the thin layer of oil formed between the curved surfaces. Now calculate the radius of the smallest dark ring. See, both the interfering waves are reflected from the denser medium. Why? Because see, here there is oil. Oil will become denser, glass will become denser, no case of air, hence no additional path will be there on reflection. Now, the formula you will use is for normal incidence, path differences 2 mu t lambda by 2. And then P be the radius of this ring, then 2t is equal to P square upon R. Or you must be remembering this formula as 2t is equal to Rn square upon R. So instead of Rn square, we have put P. Now, simplify these two expressions. What you can do is you put the value of t from here in this expression above and normalize the expression, put the values that you have been given in the numerical, change the units, and you get your answer. Newton's rings are observed by keeping a spherical surface of 100 centimeter radius on a plain glass plate. If you have been given the diameter of 15th bright ring and diameter of 5th ring, what is the wavelength of light? Very simple. Lambda is dn plus p square minus dn square upon 4pr. D15 has been given to me as 0.590 centimeter. D5 is 0.336. P is 10. Newtons are observed and the diameter of the 15th and the 5th. So 15 minus 5 is 10. This 10. And R I have been given as 100 centimeter. I straight away put the values and I get my answer. One small trick, since dn square is there, use the formula a square minus b square is equal to a minus b into a plus b. It will become very simple and you get your answer. The lower surface of a lens resting on a plain glass plate has a radius of curvature of 400 centimeter. When illuminated by monochromatic light, the arrangement is producing Newton ring, and the 15th bright ring has a diameter of 1.16 centimeter. So you have to calculate the wavelength of monochromatic light. It is 116. No, 1.16. So diameter of nth bright ring is dn square is equal to 2 into 2n minus 1 lambda r upon mu. N is 1, 2, 3. You have been given n as 15. 15th bright ring. D15 is this much. R 400, radius of curvature. Mu equal to 1. That means no medium. It is simple air here present. Put the values and you get your answer. Newton's rings are observed normally in reflected light of wavelength 6000 angstrom is itna radius of curvature of the lens and thickness of the film. See, for dark ring, dn square is equal to 4n lambda r, or r is dn square upon 4n lambda. Put these values, n equal to 10 for the 10th dark ring, and you get the answer. For thickness of the film corresponding to a ring of diameter d, 2t is equal to d square upon 4r. Light containing two wavelengths, lambda 1 and lambda 2, fall normally on a plano-convex lens. If nth dark ring due to lambda 1 coincides with nth plus 1th dark ring due to lambda 2, you have to prove that the radius of the nth dark ring is given by this much. See, radius of nth dark ring is Rn is equal to n lambda r, and n plus 1th, it is dn square is equal to this much. So n is lambda 2 upon lambda 1 minus lambda 2. Put this value of n in Rn formula and straight away you will get the answer. It is very easy because you see they have given that they are coinciding. So the equation becomes very simple. Coincides means at the same place. Two plano-convex lenses, each of radius of curvature 100 centimeter have been placed. Their curved surfaces are in contact. So what will happen? Then thickness of the air film, T1 will be due to this upper one and T2 due to the lower one. So total T becomes T1 plus T2. Formula for T1 is T1 is d square upon 8R, and you put this value here in the expression, and simply for normal incidence, the condition of nth dark ring is 2T equal to n lambda, and radius of nth dark ring is given by n lambda r1 r2 upon r1 plus r2. We have in fact just derived this expression in one numerical up, and you get it here. Put the values for n 20th dark ring and 10th dark ring. So it is C square root of n. So 20th minus 10, and you get lambda has been given to you r1 r2. Since r1 is equal to r2, so you put the numerical value and you get your answer. Convex surface of radius 300 centimeter of a plano-convex lens rests on a concave spherical surface. If the Newton's rings are viewed with reflected light of this much wavelength, calculate the radius of 12th and 13th bright ring. See, now the formula which we have derived right now up is giving us the radius of the nth dark ring and nth bright ring. We know these formulas. We put the values that have been given to us from the numerical here in this question and simply solve. Radius of 12th dark ring comes out as this much, and radius of 13th bright ring is coming out this much. The question is asking how many fringes are appearing. So what we will do, no, they have just asked, okay, you have only been asked the radius of the 13th and the 12th ring, okay. In Newton ring experiment with the film observed with light of this much, difference of square of diameters has been given to you. Wavelength of light changes to this, liquid of refractive index is introduced, radius of curvature of convex surface of plano-convex lenses doubled, okay. Now in Newton ring experiment, the formula is dn plus p square minus dn square 4p lambda r is radius of curvature, mu refractive index. For successive rings, that means one after the other. That means, suppose I say second and first. So 2 minus 1, 1. Third and second, 3 minus 2, 1. P will be equal to 1. Only trick in the numerical. Simple, put the values. You can simplify it either by dividing or even cross multiplying. It makes no difference. You get the answer. Then for refractive index case, put the formula of mu and you use the values that have been given and you straight away get the answer. And radius of curvature of the plano-convex lenses changed, doubled, I think. So in that case, you just put here r dash has been given to us as 2r. Radius of plane has been doubled. And this you subtract, you get your answer. Thank you.